what I'm going to try to argue today is that we can start to understand psychiatric disorders meaningfully, perhaps even most meaningfully, from the perspective of brain circuits. And that by understanding them this way, we can get potentially new and very exciting, very different purchase on treatment mechanisms and on the creation of novel treatments. Some of you may no doubt already believe this in the work you do or in the things you read, but let's just, as we go through this, suspend disbelief and see if I can prove this to you in some of the findings we've published now over the last couple of years. So those are the disclosures. Let me just start then by contextualizing why even take this approach and why now is a good time to do this. Let me help you see the perspective from psychiatry by going slightly outside of psychiatry, and specifically going to the year 1987, now almost 30 years ago. A couple interesting things happened in 1987, one of which has nothing to do with biomedicine per se. The Simpsons came out, just to give you a kind of a social anchor as to what happened. AZT came out, which was the first HIV medication approved for HIV. And Prozac came out, which was not the first medication approved for depression, but was the first in a class of selective serotonin reuptake inhibitors, or SSRIs. And the class is interesting in a number of ways I'll highlight in a second, but that was certainly a milestone, the approval of Prozac within the United States. If you fast forward to now, in all these fields there's been progress all along. Actually, this isn't even the most recent progress. There's been lots of new things on various regards. Biomedicine has seen those same gains that you'd expect over time. We're now talking, for example, these are headlines pulled from the New York Times about cures for HIV. But you contrast those with mental illness, and it's quite striking. There's really been no change in how common or disabling our illnesses are, and really we're talking about any mental illness. It's quite striking that across this range there's been very little progress, period, in terms of treatment and to some degree in terms of understanding. But certainly where the rubber meets the road is helping people get well faster, helping them get well earlier, and doing it in a more targeted or more effective way. Interestingly, the thing that stood out for Prozac that really made it a commercial success was really related to how it is delivered to the community, and that is it was now starting to be prescribed by non-psychiatrists because it had a lower side effect burden, and the innovation was direct-to-consumer marketing. So neither of those really are things ultimately that we can say was a great success in any regard. If that's the perspective that we're coming from, then looking at other areas of biomedicine and society that have seen progress, it's even more daunting when you look at this graph here. What this is the quantification by the World Economic Forum in a recent report of the cost associated with illness. And the cost associated with illness here is not just the care for the illness, but things like lost productivity at work, and impact on societal processes. And the y-axis here is plotted in trillions of dollars, and this is estimated worldwide by 2030, 2030 being not that far away from now already. And what you can easily see there is that mental illness pops up above the rest of these chronic non-communicable diseases as something that is associated with particular burden. In fact, if you look at the only other large bar, COPD, which is particularly driven by smoking in the third world, if you simply decrease smoking, that bar would go to the level of cancer, cardiovascular disease, or diabetes. And yet we think much more about these other disorders as being major high-impact disorders and seem to forget often about the importance of mental illness. And similarly, we've seen a lot of progress in all of these other areas and not so much in mental illness. So if you just think about the size of these bars and what a movement of this bar by even a small amount, which is what we're hoping to get to, even just incremental improvement as a course of the research, it would have a huge financial and societal impact. How does one get there? Well, you can start by trying to look at psychopathology, which we've been doing now in various forms since the days of Freud and before, and trying to make sense of it, trying to understand out of this range of psychiatric illnesses that we can kind of say something is wrong with this person, how do we start breaking up that space into some sort of a meaningful bins or meaningful disorders or syndromes that allow us to get some purchase on biology and treatment. What we've done in the field is something like this. We've started with DSM, or the Diagnostic and Statistical Manual, which is a symptom-based definition of disorders. We went from DSM-3, DSM-4, and most recently DSM-5. The implicit assumption here is that by looking at symptoms and clusters of symptoms that were fairly arbitrarily put together in kind of a strange and arbitrary decision rule, we can define a disorder that implicitly is therefore distinct from other disorders defined by other criteria. So that already brings in certain assumptions, but we've made progress here. We've gone from Roman numerals to Arabic numerals, and we're going to even enter the decimal system at some point. So that's progress of its own. There's been other progress in other domains. Recently, in the past 5-6 years, the National Institute of Mental Health has released a concept called RDoC, or Research Domain Criteria, which seeks to study dimensions of brain function as they relate to symptoms and psychopathology and things like genes and molecular mechanisms and so forth. This seems on its face to make sense that you should study the brain and brain processes, but remember, this too has assumptions behind it that are untested. For example, that these things can even exist dimensionally, abnormalities can exist dimensionally across a wide range of psychopathology, and that somehow putting all this together could make sense. It's a nice hypothesis, but it's not yet proven. You can hybridize these in a way. You can say, well, maybe symptoms are the thing that you can look at, but in a more RDoC-y way, so that you can look at a particular focused set of symptoms and vary those dimensionally across a group. But ultimately, all of these top-down approaches lead you to look like this person basically pulling out her hair for lack of a clear first principles answer to that question. Our answer then is to start by looking at the brain in as much of an unbiased way as we can, and then seeing what we can start to see as patterns that recur, what we can start to push around on a circuit level, and try to understand mechanisms and new directions from there. So let me just start then with trying to answer the first question, which is, are neural circuits in the brain the substrates of mental illness? And let me just be very clear here about what I mean by neural circuits. Here I'm looking at large-scale distributed circuits that lie across anatomical regions that mediate some particular brain function. You can also think of circuits at the micro level and at various other levels as well that I'm not going to address today, but they all contribute, I think, to the same picture. And I'll specifically start by looking at meta-analyses of imaging data that cross traditional diagnostic boundaries, if you will, starting from the 30,000-foot view, and I'll show you in a second why that's valuable, and then descend into particular disorders from there. Why would we look at meta-analyses? Well, meta-analyses allow us to do things like this. It allows us to do, first of all, quantitative summaries of imaging data, when imaging data themselves are acquired on small sample sizes, which has been the tradition out of need, essentially, across the history of the field. So most of the studies have been in probably an average sample size of about 20 per group at best, and it allows us to quantitatively summarize over them for a disorder compared to controls, let's say. But it also allows us to compare disorders to each other, and that's what we did in our first meta-analysis. So here we've compared negative emotional processing in anxiety disorders, post-traumatic stress, social anxiety, and specific phobia, disorders that differ quite dramatically in their severity, but are all conceptually unified as anxiety disorders. And here we found that there's overactivity in red of the amygdala and in the insula in patients compared to controls across these disorders when they were processing negative emotional information. None of these disorders were put in the same study, and only through meta-analyses were we able to compare them. as I mentioned, the implicit thing with DSM diagnoses is that by defining a diagnosis based on symptom, you implicitly say that it is distinct from another diagnosis defined by other criteria. And then what people have done is essentially take your patients for some disorder that you're interested in, take your controls and compare them, and never look at specificity, never look outside their window, which leads to a lot of very skewed conclusions driven by our own biases rather than by understanding the brain. And here already you can see the first bit of evidence, and this is really one of the first transdiagnostic imaging studies, suggesting that there's a lot of commonality between disorders. In fact, if you have healthy subjects undergoing fear conditioning, which is a conceptual model of anxiety, you see very much similar things, that you activate the amygdala and the insula. We then turned a few years later, once there was enough data, to depression and did the same kind of meta-analysis and found here overactivity in the amygdala, the insula, and the dorsal cingulate. So now we're looking across all mood and anxiety disorders. This then led us to an even more bold possibility, which is to consider whether we are in fact missing a forest for the trees. By looking at individual disorders, we're missing the very intriguing possibility that there is in fact a common biological substrate that rides across mental illnesses. You already saw excuse me, you already saw here within the mood and anxiety spectrum that there are a lot of similarities, but what about similarities that ride across psychiatric disorders? There are a lot of things that are similar across psychiatric disorders. For example, the dysfunction with life, the inability to sustained complex attention-demanding activities as well. Things of that nature that may actually have a common substrate across illness. The trick here, however, is how to study this. The approach we took in particular is again a meta-analysis now across all major psychiatric disorders in adults. So this is representative of studies of schizophrenia, bipolar disorder, major depression, anxiety, OCD, and substance dependence. So casting our net as wide as possible, as wide as the existing data would allow, and this ultimately included 193 studies that reported whole brain data covering roughly 16,000 individuals split between patients and controls. But the key here is what we looked at in our meta-analysis, which was voxel-based morphometry, or a measure of gray matter volume. Why would we do this? Well, it turns out that not only are we biased in how we study disorders in terms of comparing patients to controls in fairly sort of distinct groups based on symptoms, but never really looking at specificity, but also the kinds of tasks that we give our patients are very biased by what we think the disorder is about. So, for example, if you were to study schizophrenia, you're much more likely to give a cognitive task than if you were to study depression. If you were to study depression, you'd be much more likely to give an emotional task than if you were studying schizophrenia. And I can guarantee you that's not because people have carefully looked at these tasks in a comparable way across groups and found that the effect sizes are just different, and therefore they go with where the effect sizes are. This is entirely driven by our own biases. Looking at gray matter structure as a starting point here allows us to look in an unbiased way, independent of the particular task that is used, across disorders, and so is a nice starting point for looking at common mechanisms. But moreover, everybody has to acquire structural data if they're getting any other kind of functional data, and so it actually allows us to look at quite a large number of studies, and as you can see, it's the largest neuroimaging study of psychiatric patients to date. So the interesting thing then is what happens when you put this into the meta-analysis. What you can see here in blue-green is the main findings, which is loss of gray matter along the medial prefrontal cortex, the anterior cingulate, the bilateral anterior insula, and the thalamus. So this is all patients put together. You can then say, well, maybe the schizophrenia sample, the psychotic disorder sample, which is about half or so of the studies, maybe that's what's driving this. So we split this into the first common sense split, which is into psychotic and non-psychotic disorders. That's one of the first major splits that you see when you look at symptom variation across large swaths of people. And what you can see immediately here is that the gray matter loss is greater in psychotic disorders and non-psychotic disorders. However, there's a lot of similarity. And while their greater loss is interesting, in a sense that it's interesting to see where it happens and that it happens in psychotic disorders, it is also perhaps not surprising in that schizophrenia is a more severe disorder than depression or PTSD in many regards. However, it's the overlap that's most interesting. The overlap here between psychotic and non-psychotic disorders is found in only 3 regions in the brain: the dorsal anterior cingulate and the bilateral anterior insula. In fact, if you plot the likelihood of gray matter loss here on the y-axis, it's similar across these 3 regions and occurs in a graded way throughout these illnesses. And what you can see from this is that while there's greater gray matter loss in schizophrenia, it's seen in all of the illnesses to roughly similar degrees. You can see there's maybe a 3-fold difference overall between the disorder with the least and the disorder with the most gray matter loss. The other thing is, if you lose gray matter in one of these regions, you're more likely to lose gray matter in the other region, suggesting that what we have here is a network effect. In fact, these aren't 3 random regions, but these are 3 very well-studied interconnected regions that form a functional network we understand quite well, and one that it turns out relates to a number of functions I'll highlight in a second, but allow us to already start to hypothesize what this might mean, what gray matter loss here might mean. I should mention that there is a finding here of increased gray matter, but that was really just in the striatum, and that was primarily driven by antipsychotic use in psychotic disorder patients. So these 3 regions, what do they do? What does this network do? Well, it's been termed the salience network, or singular opercular network, because it's activated in functional tasks, in fact, almost every functional task, anytime there's an attention-demanding or control-demanding event that's happened. So that could be cognitive, so I can imagine working memory load or conflict or some other kind of executive function tasking event has happened, so it needs you to, this is sort of a warning flag that goes up and needs you to ramp up control to deal with this. It could also be on the emotional side, so something emotionally salient has happened, a particular piece of negative information or positive information that then leads the organism to respond accordingly. That led us to wonder then whether gray matter structure, the amount of gray matter in this network, is related to executive functioning, which is one of the capacities that this network has been implicated in other imaging studies in healthy people. So we looked at we looked at healthy subjects, a large number of healthy subjects, who had received a behavioral battery of cognitive tests, and we found that within the healthy range even, less gray matter volume in this network was associated with poorer executive functioning, but no difference in terms of general response speeds or your basic ability to perform these tasks. So even within the healthy range, let alone falling off the healthy range below healthy subjects, you can see that less gray matter leads to worse executive functioning. Executive dysfunction is something you see across psychiatric disorders, in fact, in a manner very similar in its severity to the graph I showed you of gray matter loss. So it's worse in schizophrenia, less so in bipolar and depression and so forth. So this leads to new hypotheses, which we're testing now, looking at similar meta-analyses of executive function tasks, and we're finding, in fact, results very congruent with this. But these are not yet published. Are there, within this meta-analysis, disorder-specific markers? Well, it turns out that there are, but they are more the exception than the rule. And the way we found this is by doing further partitioning of these disorders in a manner, again, consistent with how people have divided symptoms in broad transdiagnostic data sets. And those have been divided into externalizing, internalizing, and bipolar symptoms. And when you compare disorders grouped in a similar manner here, you see that the hippocampus and amygdala comes out in every contrast of internalizing to externalizing or bipolar. And further, if you split up the internalizing into depression and anxiety, you find the same gray matter loss in the amygdala and the hippocampus. and that is driven by depression. So the only real clear or convincing disorder-specific finding here is the amygdala and hippocampus gray matter that's driven by depression. Otherwise, the story is actually more forest for trees. So let's start going from then the 30,000-foot level on down to look at individual disorders and see if we can start getting an idea of some of the circuits involved and where things might be more mechanistically tied. We published a study recently on comparison of connectivity and activation in post-traumatic stress and generalized anxiety disorder. Why look at those two studies, and what do those two disorders rather tell us? Well, on the one hand, these two disorders share something that's seen in a range of mood and anxiety disorders, which is an elevation in a fairly non-specific way of both anxiety and depressive symptoms. You see that in both PTSD and GAD. GAD, for those who are unaware, is essentially a severe worry disorder where the worry just takes over your life and interferes with your life. There are differences. For example, fear-related memory deficits have been hypothesized to be important for PTSD, but not GAD. This may be one of multiple things that might differ between people with PTSD and GAD. So while they may share certain things in common, they also differ from each other. In fact, people within the disorder also differ from each other. So it's not just disorder-based differences, but they may be individual differences within a disorder. How does one start to think about these areas of difference? Well, if memory is a core component of this, we understand a lot about memory. Can we maybe look at some of those memory regions and start to understand these potential distinctions better? One of the regions I mentioned in passing about the gray matter volume findings is the hippocampus. The hippocampus has been implicated in slew and slews of work looking at humans, looking at animals, in a range of mnemonic processes. But there's been recent work in the rodent and then a little bit in humans showing that actually the hippocampus is not one structure, it's at least two or three. And those two or three structures can be thought of as differing along the long axis of the hippocampus. So the C-shaped structure that you see there is the rodent hippocampus, and you can see that the dorsal hippocampus in sort of purple-blue which is analogous to our posterior hippocampus. It's more connected to regions involved in memory and mediates the cognitive memory related processes such as fear-based memory, whereas the ventral hippocampus is more related to emotional structures and has been implicated in anxiety and not as much in memory, though that is not a perfect distinction. That fairly good animal literature led us to look then at the human literature. And around the same time, a study was published looking at the anterior and posterior hippocampus in humans, and found that the posterior hippocampus was connected to the default mode network, which is seen here in the medial prefrontal cortex, the PGACC or pregenual cingulate, medial parietal cortex, the posterior cingulate, precuneus, and the hippocampus. And that this was more connected to the posterior hippocampus than the anterior hippocampus, fitting with the ideas from animal work. The default mode network has been related to memory processes in humans for a while. Whenever you're focusing on autobiographical memory, recalling events, you activate the default mode network. So this led us to wonder then whether the relationship between the hippocampus and the default mode network, the hippocampus being part of the default mode network, was related to PTSD and not GAD, under the premise that PTSD has more of a memory component than does GAD. So here is a mass of this network that we used. And our first finding here is that compared to healthy subjects, patients with PTSD had less connectivity, specifically in the posterior hippocampus, to various regions within the default mode network. You can see here the contrast from healthy people. But again, as I mentioned, contrasting with healthy people is only so useful. We really want to look at specificity to make some of these arguments more cogently. And so we looked at GAD patients scanned in the exact same way and found that they did not differ from controls in terms of the hippocampal connectivity with the default mode network, but did differ from PTSD patients. Looking at the default mode network is not just a matter of looking at its connectivity. It also shows a hallmark pattern of task activation, or really deactivation, in that it turns down in a task-independent manner every time you focus on external stimuli, the outside world. What happens is you engage attentional resources, take focus out of the internal world, thinking about yourself, sort of self-focused meditation, autobiographical processes, and so forth, to externally focused processes like doing a task or in real life having a conversation, doing your job, and so forth. So that led us to wonder whether there was a deficit in deactivation of the default mode network in a task-independent way in PTSD and not GAD, which would again go towards showing a default mode network abnormality in one disorder compared to the next. And we in fact did find that patients with PTSD failed to turn down this negative going bars here, the default mode network compared to controls, and that patients with GAD did this just fine. They had no difference from healthy controls, but did differ from PTSD. Again, suggesting that one way to understand these disorder differences, which could also be understood as individual differences, is with respect to the function of the default mode network, and arguably, memory is an important process. To kind of finish up the story on the neural circuit mechanism of illness side, and staying on this topic of cognition, we also looked at whether cognitive dysfunction and cognitive circuitry was important in the ability of patients to respond to treatment. Here, so far, I've just been showing you mapping of the brain across disorders. What about actually treating these individuals? So we looked in a study called iSpot-DEER, an international study to predict optimized treatment in depression, to the study of 1,008 depressed individuals, assessed pre-treatment in an unmedicated state, then given one of 3 antidepressant medications that are standard use antidepressant medications. It was escitalopram, sertraline, and venlafaxine, and then reassessed both clinically and biologically afterwards. We looked at their baseline cognitive task performance and saw whether it predicted change in clinical symptoms, specifically remission of clinical symptoms, when they were actually treated with antidepressants. And what I'll show you here is a z-score that is relative to a healthy norm. So 0 here means that they're performing at the level of controls. Below 0 means worse than control performance. Above means better than control performance. And I'm going to split here by whether patients went on to remit in filled bars, in open bars, or not remit with treatment in filled bars. You don't have to go through this in great detail in terms of looking at the headings, but getting kind of a global gestalt here, what you see is that there's a variety of tasks that tap a variety of mental processes, and all of them show a similar pattern, which is that there's generally lower, about a quarter to a third of a standard deviation on average lower, cognitive task performance and things related to cognitive task performance in depression relative to controls. It turns out if you actually cluster these data, they're actually driven by a subgroup. So it's only about 25 to 30% of depressed patients who have a pretty significant cognitive impairment, and that's on a level of half to 1 standard deviation below controls, whereas many patients perform similarly to controls. So already you can see within a disorder there's quite big differences. Some people are much more impaired than others, and if you just average across the whole disorder, you don't get that picture quite accurately. The other thing that differs is if you look across a variety of these tasks, those patients who went on to remit had more similar performance to controls than patients who went on not to remit. So the more healthy your brain is at the level of cognitive task performance, the better you do with treatment, even with the same level of clinical severity on the level of symptoms in depression. And you can also see that this is not particularly specific to one process. Attention, psychomotor response, information processing, memory, they are all related to treatment outcome. So more intact cognition, better outcome with treatment. And the same thing is seen at the brain level. This is activation in a subset of these individuals who were imaged. About 10% were imaged, and this is with a go, no-go task. And you can see prefrontal activation that was greater in people who went on to remit than those who did not. The next question that should come to mind then is, what happens with treatment? Does it change cognition? So cognition is something in cognitive systems are abnormal in psychopathology. The degree of abnormality relates to treatment outcome. The more abnormal, the less positive your treatment outcome with standard antidepressants is. What happens with treatment to those measures? Well, in the studies I mentioned, we looked at these individuals before and after treatment. We also had data on controls, 336 controls, who were assessed at the same interval so we can control for practice effects. And there was no differences clinically between medications or, for that matter, here with cognition. The picture that we saw then when you split it up into change in task performance in healthy individuals and change in depression, furthermore splitting depressed patients by those who went on to remit and those who did not, is a series of parallel lines for executive functions writ large. Attention, response inhibition, verbal memory is just 3 examples, and the parallel bars here, the parallel lines here, mean that from baseline to post-treatment at week 8, there was no change in the deficit in cognition in patients relative to controls, even though they were treated and even though some of them remitted. So overall, there's very little change in cognitive dysfunction analyzed at a group or individual level with treatment, suggesting that this is something that is actually quite persistent and may in fact underlie risk for relapse of depression, which we know is a chronic relapsing and remitting disorder, and is not currently targeted by 3 conventionally used antidepressants. So already we need to start thinking about, if this is a really important system as it seems to be, how do we actually target it in different ways? Well, to target it, I think we need to start thinking more generally about the concept of circuits as targets for therapeutics. But it's not quite so simple. And let me illustrate that in a series of studies we did recently that get it. It's a very basic conceptual issue, which is, of all the stuff that we see with imaging, what is actually meaningful? So we've talked about the default mode network. Here, one of the most common things that has been seen ever since, for 20 years, ever since imaging is functional imaging has come to life, is that the default mode network turns down with attention-demanding tasks, and with that, a series of regions in the parietal cortex, the frontal cortex, the insula, the cingulate all turn on. So it's a network of regions turning on, network of regions turning down, and you can even see that at rest, where in some data, depending on how you analyze it, there's a yin-yang relationship between the default mode and these sort of task positive or executive and salience networks that I'll discuss in more detail in a second. It's not just blood flow where you see this electrophysiologically as well. This is ECOG data showing that, again, when you engage in a task, power is increased in these frontoparietal networks and decreased within the default mode network. That has led people to hypothesize a model wherein the frontoparietal executive network, the anterior cingulate, anterior insula, and anterior prefrontal cortex salience network that turn on with tasks, what their effect is in terms of creating effective and goal-directed cognition is to decrease activity in the default mode network that is part of this internal mentation process. So that seems to make sense. That looks like an explanatory story. That sounds mechanistic. The unfortunate reality is that it's a just-so story. And it's a just-so story is because, for those who are familiar with this really wonderful set of short stories by Rudyard Kipling, is that it's internally consistent. It seems to make a lot of sense, but it could have absolutely no basis in fact. And the reason that we don't know whether it's reality or just so story is because all of these data come from correlational imaging, seeing things happen and things go up, things go down, and telling a story, but not actually knowing whether there's any cause or effect there at all. Specifically, we don't even know whether the default mode network is under causal control of the executive or salience networks, and if so, how this happens. This is a really critical question just from a healthy brain mapping perspective, understanding how the brain works and brain organization is causally mediated, but also a fundamental question for treating these disorders which implicate these networks. That is, if you wanted to drive default mode network up or down, where would you target? Could you target anywhere that turns up? Is that equipotent with respect to control of the default mode network? Does any of it control the default mode network? So to try to answer those questions and subsequent work from there targeting other regions as well, we have combined TMS or transcranial magnetic stimulation with fMRI, as seen here. You see the coil, the wire running into this little figure 8 coil, which is the TMS coil, inside a birdcage head coil, and that is put into the MRI machine, and that's how we acquire data on brain activation that happens in response to single or repetitive pulses of TMS. What TMS does is it engages the brain region being targeted, so it's a non-invasive way of stimulating the brain. It creates a burst of activity in the cortical region underneath the coil. So what you can imagine here is that you stimulate some region, it activates some bit of prefrontal cortex, as an example, and through the interconnections that might change, the strength of those interconnections might change during a task, but through those interconnections, through the network mechanisms related to the region that you're targeting, you can look at the downstream effects, and that is, in other words, the causal influence of the region you're targeting on other regions by virtue of being able to externally manipulate brain activity. Human neuroscience has been entirely based, or very, very heavily based, I should say, outside of things like lesion studies, on the use of correlational imaging. There's been some TMS work more often than not, in fact, overwhelmingly, not with brain imaging at the same time. And by marrying the two, you can really start to get at some interesting answers about causal mechanisms of circuit control, and therefore get an idea of how you can get to novel interventions. So let's go back to our conceptual model here of the executive and salience networks turning on and turning down the default mode network. We used concurrent TMS and fMRI, doing single TMS pulses just to transiently activate and probe regions within the middle frontal gyrus that either corresponded to the executive network in blue or the salience network in red here. And what you can see is that these two regions, more anterior and more posterior middle frontal gyrus, are within the same anatomical structure, in fact only a couple centimeters apart from each other, but are part of two different functional networks identified with fMRI. So then the question you would want to ask at this point is, when you activate each of them, which one has an effect on the default mode network? And specifically, we hypothesize that by activating one with TMS, we should see greater negative coupling of these networks, which is what you see when you engage in a task. In fact, that is what we saw when you activate a region in the prefrontal cortex with TMS, but it was specific to the frontoparietal executive network. You can then flip the coin on the other side and say, what happens if you transiently inhibit each of these regions using low frequency or 1 Hertz repetitive TMS? So here we did repetitive TMS to inhibit that region, and then looked at the changes in the resting connectivity and resting activity, rather, of the default mode network. And you're expecting then a disinhibition if you're getting rid of the control node here in the default mode network causal control system. In fact, that is again what we saw, and again only with the executive network node that we manipulated. So the answer to the question that we posed a moment ago is, yes, the default mode network is under causal control, but it's specific to one of two structures we interrogated within the middle frontal gyrus, and specifically one that's part of the executive network. That led us to wonder whether this could give us some purchase on RTMS as a treatment for depression, and specifically whether starting to think about how these circuits relate to each other can give us some ideas about how we can both understand the mechanisms of treatment and get to novel interventions. What you see here is a measurement, is a location rather of the stimulation points for the executive network. Here, unfortunately, colors are switched in red, and the salience network in blue, anchored relative to the motor cortex in white. Why would you want to do that? Well, why would you want to anchor it to motor cortex? A large part of the RTMS literature over the past 20 years for depression has used motor cortex as an anchor point and gone 5 to 6 centimeters anterior of the motor cortex and done stimulation there, calling that the dorsolateral prefrontal cortex target. The reason that they did that is because motor cortex is easy to find. You can cause a thumb twitch on the opposite side of the body, whereas prefrontal cortex in any other way, certainly DLPFC, has no overt sign of a change in behavior when you stimulate it. So you can only really anchor to the thing that you can see when you don't have imaging, for example, to help you get there. And as I mentioned, stimulation has been done at high frequency, 5 to 6 centimeters anterior of the motor strip. Moreover, this type of intervention has been FDA approved in 2008, but at that point had no clear or even known mechanism associated with it that made sense for what you were targeting in the brain. However, this actually presents a really interesting opportunity. Not only is it an interesting opportunity to understand how a treatment works, but this treatment, unlike every other treatment in psychiatry, is very, very specific. You're taking one brain region and stimulating it repetitively over weeks. So you know what you're doing because you are putting something very, very specific in, and you can literally quantitate every single pulse, the response to every single pulse if you wanted to. And yet that had not been done, and we didn't understand, therefore, the mechanisms of RTMS. So it's a really exciting opportunity for getting some purchase on intervention mechanisms. Turns out, when you look at the distance between motor cortex and the executive and salience nodes, the executive node that controlled the default mode network was 5 to 6 centimeters anterior of the motor strip, and moreover, the default mode network in data I've shown you and other data has been implicated in treatment mechanisms or in the treatment response in depression. Leading us then to wonder whether RTMS changes the interactions between the executive and the default mode network in a manner consistent with our causal TMS fMRI evidence that I showed you a moment ago. So here we partnered with Connor Liston and Mark Dubin at Cornell to look at data on resting connectivity for patients who got the left DLPFC RTMS treatment, the FDA-approved NeuroStar protocol for depression. What we found is that RTMS decreased hyperconnectivity relative to controls in the default mode network and between the executive and the default mode networks. So already you can see that RTMS impacted the exact same circuitry we would hypothesize from our TMS fMRI study. So that was pretty exciting to see. But even more exciting is the idea that with respect to connectivity, the more abnormal, the more hyper-connected, the abnormal relative to controls, the default mode network and the executive and default mode network were, the better the outcome. In other words, unlike with conventional antidepressants, here the more abnormal the brain, the better you do. With conventional antidepressants, the more cognitively intact and more normal activation that you see, the better you do. So this starts to suggest that we can in fact think about circuitry and think about circuitry flexibly, both in our ability to target it and also whether we're trying to increase it or decrease it, but that there may be options specifically by targeting circuitry, in this case with TMS, for improving the disorder, improving the clinical state for patients who would otherwise not respond to conventional interventions. So that actually gives us the perspective of neural circuits as the targets and allowing us to alter neurocircuits as a mechanism for treatment that is not otherwise addressed by current interventions. Interestingly, not everything is coming up roses in the world of circuit modulation. It turns out that the hypoconnectivity within the frontoparietal network in patients relative to controls was not ameliorated by RTMS stimulation within the executive network, even though you are stimulating there. What we saw changed more is the relationship to the default mode network and the default mode network itself, suggesting that perhaps approaches using multiple coils may be important for fixing the broad range of circuit abnormalities, and not just the relationship to the default mode, but that within the executive network as well. So putting this then together and wrapping up, we are now starting to understand what circuits to think about in the brain, how to target them in novel ways, understanding causal mechanisms with TMS fMRI. We're also understanding the limitations of this, in that TMS, as underused as it has been, still can only target superficial cortex. So that's most of our cortex is dorsal, accessible, superficial cortex, but there are deeper cortical regions that are not currently targetable, and they're very deep, small structures like the amygdala and the ventral striatum, which are just simply not targetable with current methods. That's led us to start a new initiative through the Stanford Neurosciences Institute, which I co-direct, and that aims to develop tools and understanding that would allow us to stimulate and modulate anywhere in the human brain, both for understanding how the brain works and as a method of creating novel interventions. We call that neurocircuit as the name of this project, which involves, on the one hand, a lot of tool building, so new TMS methods that go deeper, focused ultrasound, but also couching this within a connectomic perspective, understanding cause and effect within the connectome in humans and in other animals, to allow us to really understand when might you want to use multiple coils, which kind of region connects to what other kind of region in a causal manner, and using that to inform our tool building. How this then will come together, I think, in the next perhaps 5 or 10 years, not even a very long time, is that we'll get a good understanding of how to use circuit modulation, for example, with RTMS, and that can target a variety of different brain regions, and that will improve as we improve technologies. And that may be fine by itself, but we also have to remember that we've been doing a lot of things, for example, like psychotherapy or medication as a field, that improve people's functioning and symptoms, and that we can learn something from that and harness the effects of that with TMS. So that may literally look like combining interventions, or maybe just simply taking the concept that you need to engage emotion while you alter executive control to allow us to manipulate behavior in a task-type manner while doing our TMS. And you know what? Let's maybe just throw some drugs on there too, except this is not going to be your garden variety antidepressant. But now, by thinking about plasticity as the core mechanism that we're engaging in order to alter circuits in a directed way, sculpted through behavior, the medications we might want to use here are going to be medications that alter plasticity per se, the ability of the brain to change, in this case with repetitive stimulation, and may only be given at the time of the stimulation treatment itself. So what this looks like then is a very different psychiatry, one that combines behavior, neurostimulation, and medication potentially, but one that is really driven by neural circuits in its core and trying to speak the language of circuits. Let me just close by thanking all the people involved in this work, and work that I didn't show as well today, that's taking this in other interesting directions more recently. Folks in the lab you can see in the upper right there, as well as a range of collaborators both within Stanford and beyond. And then, of course, our generous funders, especially the NIMH and Cohen Veteran Biosciences, the VA, and the Dana Foundation.